Alright, this next video will deal with finding the derivative of the inverse of tangent. So I wanted to separate this as I'm going to give you the derivative of all inverse trig functions. But I'm going to show you at least how to do it for the tangent function. So finding the derivative of the inverse tangent function. Well, first of all, since we're dealing with tangent, let's simply let f of x be equal to tangent of x. And remember that we define tangent of x to be trapped between the interval negative pi over 2 to pi over 2. Okay. We do this because if you remember, the graph of tangent has a bunch of vertical asymptotes. Right. So then we will let g be the inverse of x, of f of x, and the inverse of tangent of x is arctangent of x. So let g of x equals arctangent of x be the inverse tangent function. Now, to find the derivative of arctangent of x, we will actually use a fact from trigonometry. So, if you recall, sine square x plus cosine square x is equal to 1. Now, if we divide everything here by cosine square x, what we have is sine square x over cosine square x. We could write that as sine of x over cosine of x, the whole thing squared, plus cosine of x divided by cosine of x, both of them squared is just 1, and then 1 over cosine square x. Now, sine over cosine is exactly tangent. Remember, tangent is equal to sine over cosine. So this is simply equal to tangent square x plus 1. And 1 over cosine square x is the same thing as secant square x. We covered this a while back when we first introduced the derivative. Okay, so I'm going to use this fact in a little bit. Now, remember, our formula for the inverse function is g prime of x is equal to 1 over f prime evaluated at g of x. This is going to be important because I don't want to use, sometimes I don't want to use the given. All right, so let's see what happens. So I have to find f prime. We're finding g prime, but before we go to find g, we have to find f prime. Now, f is equal to tangent of x. By now, you should have memorized all 6 trigonometric functions and their derivatives, and you should know that the derivative of tangent of x is secant square x. So this up here is equal to, so this is a side, so this up here is equal to 1 over secant square x. And instead of x, we're evaluating that at g of x. Okay. But now, we know, because of what I just wrote up here, that secant square x is also equal to tangent square x plus 1. So I could rewrite this as 1 over tangent squared of g of x plus 1. I simply replace secant squared with tangent square x plus 1. But now g of x, we know what that is because it was given to us up here. G of x is arctangent of x. So we have 1 over tangent squared of arc tangent of x plus 1. Now, I could actually move the square to the outside, so I have 1 over tangent of arc tangent of x, the whole thing squared plus 1. But now is where I ask you to invoke the powers of your memory. Way back when you learned what an inverse of a function was in pre-calculus, you learned that if you have f and you evaluate it at its inverse, then essentially what you get back is simply x. That's how you show that two functions are inverses of one another. If you could compose one with the other, and you get back x. So by definition, since arc tangent is the inverse of tangent, you could say that these two cancel each other out, and you simply are left with x to the second power. So this is equal to 1 over x squared plus 1. So now we have found the derivative of the inverse tangent function. So you could now say that if g is given to you as arc tangent of x, then its derivative g prime of x is actually equal to 1 over x squared plus 1. For those of you who are going to continue on to take in math classes, like if you go on to take calculus 2, this is going to come up again in something called a trigonometric integral. So you are not out of the woodworks yet. Now, I'm not going to show you all other of the trigonometric functions. I may show you one more, but I am going to give you all of them right now. So this will be in your homework. So practice makes perfect. And for sure, you need to at least know that they exist. You need to know that they exist. So a lot of math is not memorized. Math is not memorized in every single formula that you come across because, to be frank with you, there are just way too many formulas and way too many things to memorize. But it is good that you see these things and you say, hey, there is a derivative for tangent. There is a derivative for the inverse of tangent. There is a derivative for the inverse of sine and cosine, and so on. So that's the important thing, that you are able to understand that these things exist, and if you need to use them, you can look them up because they're all written down. You don't have to derive them. In any case, let me give you the derivative of the inverse trigonometric functions. Okay, so let u be a differentiable function of x. Then the following are the derivatives of the 6 inverse trigonometric functions. So the derivative with respect to x of arc sine of x, or u, I should say, doing this in terms of u, for the function u, is equal to the derivative of u divided by the square root of 1 minus u squared. The derivative with respect to x of arc tangent of u, which we just computed, is equal to u prime divided by 1 plus u squared. And I'll explain why we have the u prime here, where here we only had the 1. The derivative with respect to x of arc secant of u is equal to u prime divided by the absolute value of u times the square root of u squared minus 1. And the derivative with respect to x of arc cosine of x of u, keep saying x of u, is equal to negative u prime divided by the square root of 1 minus u squared. the derivative with respect to x of our cotangent of u is equal to negative u prime divided by 1 plus u squared. And finally, the derivative with respect to x of arc cosecant of u is equal to negative u prime divided by the absolute value of u times the square root of u squared minus 1. So notice that the derivative of arc secant of u and arc cosecant of u are only different by a negative sign. The same thing for the arc tangent and arc cotangent and arc sine and arc cosine. Okay, they only different by a negative sign. So that makes it actually easier to memorize, because if you memorize, let's say, just the left side, it's only 3 to memorize, and then you know that the corresponding ones on the other side just have a negative sign up front. They kind of always come in pairs. All right, so I will show you probably the proof of sine for arc sine. So all of these trigonometric functions are proved using a triangle like this one, where you open an angle theta. This is all in the unit circle. So imagine that you're in the unit circle. You open up this right triangle with height x, and the length of the hypotenuse is 1, because that's the radius in the unit circle. And then this side down here, by the Pythagorean theorem, you get is 1 minus x squared under the square root. Well, this is for y equals arc sine of x. Well, if we let y be equal to arc sine of x, whenever y is between pi over 2 and negative pi over 2, we have that sine of y is equal to x. That is by definition. Okay, by definition, this is the case. And now what we can do is, since we have sine of y equals x, we could take the derivative on both sides implicitly. Remember, when you take the derivative implicitly, whenever you take the derivative of a term involving y, you put either a y prime or a dy dx. So the derivative of sine, for example, of sine of y is going to be cosine of y times dy dx equals to the derivative of x, which is just 1. But now, since we're solving for dy dx, you can divide both sides by cosine of y, so you get dy dx is equal to 1 over cosine of y. But 1 over cosine of y is the same thing, again, by this rule. By this same rule, if you solve for cosine here, you're going to get that cosine of y is equal to 1 over the square root of 1 minus sine squared y. So I'll leave that as an exercise for you to actually solve this, so you could get this conversion right here. But now that you have 1 over sine squared of y, we actually have a value for sine of y. Sine of y we set up here is equal to x. So we could substitute back in the x for sine squared of y. So before I do that, let me just rewrite it so you can see what's going to happen. So we have 1 minus sine of y, the whole thing squared. Now I'm going to substitute x in place of sine of y, because that is what x is equal to. So I'm going to have that this is 1 over square root of 1 minus x squared. Now, because we are talking about a u being our input for our sign, and u is given to us as a differentiable function. I actually misspelled this differentiable. Actually, I just realized I combined the word differentiable and function, differentiable function of x. So because u is a differentiable function of x, we can use the chain rule to write. So because u is a differential function of x, we use the chain rule to write that the derivative with respect to x of arc sine of x of u, say x of u, is equal to u prime divided by 1 minus u squared, where that u prime we have here is du dx, the derivative of u with respect to x. And we must have this because remember, whenever we take the derivative of something like this, let's say cosine of 3x, by the chain rule, it's going to be equal to negative sine of 3x times the derivative of this inside piece, which is just 3. Okay, so whenever you're taking the derivative of something like this, then you get minus sine x times d dx. Always. All right, so this is how you will prove at least the first one. You could use a similar argument to prove all of them. You could simply start with the definition. And when I went from y equals arc sine of x to sine of y equals x, that's by definition of the inverse function. Remember that the inverse is, looking at the output to get the input. So here the output is y, and we're looking for the input, which was x. So if you were working with the arc cosine one, then for the arc cosine of x, so if y equals arc cosine of x, then you could write cosine of y equals x. And if you follow a similar process like I did, you're going to get this solution right here. You just have to be a little bit careful, but you will get that same solution. Okay? Anyway, let's actually do an example for actually simplifying derivatives that involve the inverse trig function. So let's differentiate y equals arc sine of x plus x times square root of 1 minus x squared. Right, so if we were looking to take the derivative of something like this, what would you do? Well, first of all, what I will do is take each piece one by one. Let me say f of x is equal to arc sine of x. Then I know that its derivative from the table up top is u prime divided by radical 1 minus u squared. We just did this. U prime divided by 1 minus u squared under the square root. So I have this derivative. And then let the other one be g of x. So that's x times 1 minus x squared. And this derivative, because of the product rule, is going to be equal to, and I'm going to use this different letters. So it's going to be the first times the derivative of the second plus the second times the derivative of the first by the product rule. So here you could let h of x be x, and you could let k of x be square root of 1 minus x squared. And that's to take this derivative. So to take the derivative of g, we have to do the product rule. Now the derivative of h is just 1, because the derivative of x is 1. And the derivative of k of x, what I'm calling k of x, well, let's rewrite this. This is 1 minus x squared to the power 1/2. So it's going to be equal to 1/2 times 1 minus x squared to the power negative 1/2. And now we have everything we need to actually write the derivative of g prime, because that's just h of x, which is x, times the derivative of k of x, which is 1/2 times 1 minus x squared to the minus 1/2, plus, from the formula, k of x. K of x is just 1 minus x squared to the 1/2 times h prime of x, which is just 1. The derivative of h prime is just 1. I'm not going to simplify this too much. I'm actually going to keep it like that. Yeah, I'm going to keep it like that. Am I missing something? Oh yeah, I'm missing something. Whoa. Let's be careful here. So yeah, I'm missing something. I have to use the chain rule on this, the inside. The derivative of the inside here, 1 minus x squared, is negative 2x. Negative 2x. So times negative 2x. It's always good to double check all of your work. So this first x comes from h of x, and then this whole piece comes from up here. Then plus this. Okay, now we're in business. All right, so now I could put everything together, because now I have that the derivative of y prime is equal to this plus this. So it's equal to f prime of x plus g prime of x. Now, I haven't done much work with f prime of x, and the reason why is because here, if you notice, u is the value of the inside of the parenthesis here, but this is just x. So this is actually equal to square root of 1 minus x squared, and the derivative of x is 1. This is because u equals x, so u prime is equal to 1. Right, so now I have everything that I need to solve the problem. So y prime is simply f prime plus g prime. F prime is 1 over radical 1 minus x squared. So 1 over radical 1 minus x squared plus g prime. G prime is equal to what? G prime is equal to negative 2 times 1/2. The 2's cancel out, so you still have a negative. So let's put the negative out here. So minus x times x is x squared times x minus 1 minus x squared to the minus 1/2 plus 1 minus x squared to the power 1/2, and times 1 is just the same. So now what I will do is I'll rewrite this second term. I'll bring it to the denominator. So that's minus x squared divided by the square root of 1 minus x squared. That's what it means to have a negative exponent. Plus 1 minus x squared to the 1/2. Now, because of the fact that these two fractions have the same denominator, I can combine them. So I'm going to write this as 1 minus x squared divided by square root of 1 minus x squared plus 1 minus x squared to the 1/2. And hopefully you see what's going on here. If we write back the denominator as 1 minus x squared to the 1/2 power now, you will see that I have this one to the power 1 and this one to the power 1/2. And if you recall from college algebra, if you have two bases and you're dividing one by the other, and they differ, and they don't have the same, I mean, even if they have the same exponent, you just subtract the exponent, so you have a m minus n. So you take from the top. So what this is going to be equal to is 1 minus x squared to the power 1/2 plus 1 minus x squared to the power 1/2. And this is because, again, 1 minus 1/2 is equal to 1/2. So that's where we get this. But now I have two of these. So this is y prime is equal to 2 1 minus x squared to the power 1/2. Because we have two things that have the same base and the same exponent. So we have two of those. And that will be the solution. So this is how you will simplify a problem that involves the inverse trigonometric functions. Yeah. Let's do some rapid fire examples. So what I mean by that is I'm going to take the derivative of all of the trigonometric functions in the following form. First of all, what is arc sine of 2x? Well, if I was to take this derivative, I will focus on this inside piece. I know that this has to be equal to u prime divided by the square root of 1 minus u squared. We just did this problem, so it's the same formula. We have a formula for these problems. I just need to find out what u is. U is this inside number, so that's 2x, or this inside expression, which is 2x. So we have to find now the derivative of u, which is u prime. The derivative of 2x is simply 2. So that means that the derivative with respect to x of arc sine of 2x by the formula is equal to u prime, but u prime is 2, we just found that out, divided by 1 minus u squared, but u squared is, u is 2x. So we simply write 2x squared. And we could simplify that a little bit more. This is going to be equal to 1 minus 4x squared. So that's how you will do a problem if you're given arc sine of, let's say, 6x cubed, or arc sine of whatever function, then you simply apply the formula. For example, if you're told to find arc sine of, let's say, x cubed plus 5, then again, you simply let u be x cubed plus 5, which means that du, the derivative, is going to be 3x squared. Or, yeah, du. So sometimes I will write du or u prime. So when I write du, I just mean derivative of u. And again, by the formula, this is u prime divided by square root of 1 minus u squared. So this is just u prime is 3x squared divided by square root of 1 minus x cubed plus 5 squared. And, you could expand that and then distribute the negative sign, but after that, the calculus step ended here when we took the derivative. Everything else now is just plugging in respectively and simplifying. Okay, that was the first example. Let's do one with tangent. So ddx of arc tangent, let's say 3x, is equal to what? Well, the derivative of arctangent we said was u prime divided by 1 plus u squared. Now, u here is 3x. U prime, the derivative of 3x is 3. So, that means that the derivative of arctangent of 3x is equal to 3 divided by 1 plus 3x squared, which is equal to 3 divided by 1 plus 9x squared. Okay? And again, the same thing applies. If you have something else besides a linear expression, you simply make whatever is inside of the parentheses your u, and you find its derivative. Okay, so let's do another one. let's say arc sine of radical x. Again, u is this inside piece, so that's radical x. The derivative is going to be equal to, and again, always rewrite it, because when you rewrite it, you could see clearly that it's a power rule problem. So it's going to be equal to 1/2 x to the minus 1/2. That is because you bring the 1/2 to the front, and then you minus 1 from the exponent. So you could rewrite this as 1/2 times the square root of x. So now we have, again, arc sine was u prime divided by the square root of 1 minus u squared. So this is equal to u prime. Well, u prime here is what? U prime here is 1/2 radical x divided by radical 1 minus radical x squared, because again u was radical x. We could simplify this actually a little bit more. So this is 1/2 radical x over 1 minus x, and I will leave it like that. I'll actually leave it like that. You could simplify this a little bit more. You could rationalize the denominator. You could do the keep change flip method as well, but I will leave it like that. It's not that big of a deal. If you were to fix it, if you do the keep change flip method, it will be 2 radical x times 1 minus x. So you could also leave it like that if you wanted to. That's not a problem. You could take the x on the inside and multiply, or you could leave it like that, because they are both under the square root. In any case, let's do a final one. So what if somebody asks you to find arcsecant of e to the 2x? We haven't taken the derivative of e in a while. Well, once again, the steps do not change. You find what u is, and you take its derivative. Remember, by the chain rule, the derivative of e to the 2x is going to be what? Well, I told you that the derivative of e to the x is simply e to the x. This is sometimes you find this in means. However, the derivative with respect to x of e to the u, where u is a differentiable function of x, is e to the u times u prime by the chain rule. So you gotta be a little bit careful. If u is a function, then you have to use the chain rule. So here we have a function, we have 2x, so we use the chain rule. So u prime is going to be equal to e to the 2x times u prime. U prime is the derivative of 2x, which is just 2. So we get 2e to the 2x. Okay? Now, we put this back together. So the arcsecant rule was that complicated one with the absolute value. So that was u prime divided by the absolute value of u times u squared minus 1. U squared minus 1. Now, u, so let me put this like this. And let me box this one out as well. U prime, we know what it is. U prime is 2e to the 2x divided by the absolute value of u, which is e to the 2x, times e to the 2x squared minus 1. Well, that is equal to 2e to the 2x. The absolute value of e to the 2x is just e to the 2x. Okay? And you're still multiplying this by e, but now it's to the 4x minus 1. You could cancel the e to the 2x and you get 2 over square root of e to the 4x minus 1. And that will be your solution. So far, we have now seen how to take the derivative of all the transcendental functions, like the logs, exponentials, trigonometric, and now inverse trigonometric functions. and all algebraic functions like polynomials, rationals, and functions involving radicals. What this means for our class and for our purposes is that now that we have all of the tools of taking derivatives under our belt, we will now move forward to seeing how the derivative is used in applications to the real world. We have kind of hinted at it with the instantaneous rate of change problem, and we had a word problem not too long ago with the acceleration and velocity of an object. We will delve now a little bit more into word problems in the next coming weeks. That is it for this particular lecture. Thank you for your time.